The inspector is correct. According to the National Electrical Code, the minimum size for parallel conductors for a 400 amp service is 600 kc mil copper. The circular mil is a unit of measurement for the cross-sectional area of a conductor. For copper, 1 circular mil is equal to 0.1963 square inches. The cross-sectional area of a conductor is directly proportional to its ampacity. Therefore, a conductor with a larger cross-sectional area will have a higher ampacity. The National Electrical Code requires that the ampacity of a conductor be equal to or greater than the load that it will be carrying. In this case, the load is a 400 amp service. Therefore, the minimum size for parallel conductors for a 400 amp service is 600 kc mil copper. It is important to note that the National Electrical Code is a minimum requirement. Local codes may require a larger size for parallel conductors for a 400 amp service. It is always best to check with the local code authority before installing any electrical equipment. When dealing with electrical installations, particularly concerning service entrances and conductor sizing, understanding the National Electrical Code is paramount. The National Electrical Code, or NEC, provides comprehensive guidelines to ensure electrical safety and proper installation practices. A common point of confusion and potential misinterpretation arises when determining the appropriate size of conductors for a given electrical service, such as a 400 amp service. In this specific scenario, the question revolves around the use of parallel conductors, specifically 3/0 copper conductors versus the code-required 600 kc mil copper conductors. The inspector's rejection of the 3/0 copper conductors is based on a correct interpretation of the National Electrical Code's requirements. The code mandates that the ampacity of the conductors must be sufficient to carry the intended load, which in this case is 400 amps. When parallel conductors are used, the combined ampacity of the parallel conductors must equal or exceed the required ampacity of the service. The crucial factor in determining the correct conductor size is the circular mil area. The circular mil is a unit of measurement used to quantify the cross-sectional area of a conductor. This area directly relates to the conductor's ability to carry current. A larger cross-sectional area allows for a greater flow of electrons, thus increasing the conductor's ampacity. The relationship between circular mils and ampacity is defined by the conductor's material, in this case copper, and its insulation type, as well as the installation environment. The National Electrical Code provides tables that specify the allowable ampacities for various conductor sizes and types under different conditions. For a 400 amp service, the National Electrical Code stipulates that a minimum of 600 kc mil copper conductors are required when using a single conductor per phase. When using parallel conductors, the combined circular mil area of the parallel conductors must be equivalent to or greater than that of a single 600 kc mil conductor. The rationale behind this requirement is to ensure that the parallel conductors can collectively handle the 400 amp load without exceeding their ampacity ratings and potentially overheating, which could lead to insulation damage or even fire. The ampacity of a 3/0 copper conductor depends on its insulation type and the installation conditions, but it is typically less than 200 amps. Therefore, using two parallel 3/0 copper conductors per phase would provide a combined ampacity of less than 400 amps, which is insufficient for a 400 amp service according to the National Electrical Code. In contrast, a 600 kc mil copper conductor has a significantly higher ampacity, exceeding 400 amps under most conditions. Therefore, when using parallel conductors, the equivalent circular mil area must match or exceed that of the 600 kc mil conductor to meet the National Electrical Code requirements. It is important to remember that the National Electrical Code represents the minimum safety standards. Local jurisdictions may have additional requirements or amendments to the National Electrical Code that are more stringent. It is always best practice to consult with the local electrical inspector or authority having jurisdiction, also known as the AHA, to ensure compliance with all applicable codes and regulations. Neglecting to adhere to the National Electrical Code requirements could have serious consequences, including electrical hazards, equipment damage, and potential liability. Proper conductor sizing is essential for ensuring the safe and reliable operation of electrical systems. Therefore, it is crucial to understand the National Electrical Code's provisions and to follow them meticulously. In summary, the inspector's rejection of the 3/0 copper conductors for a 400 amp service is justified based on the National Electrical Code's requirement that the combined ampacity of parallel conductors must be at least equal to the ampacity of a single conductor that could handle the load. In this case, the 600 kc mil copper conductor is the benchmark, and the parallel conductors must have an equivalent or greater circular mil area to meet the code requirements. Always consult the National Electrical Code tables and local authorities to ensure compliance with all applicable regulations. To further illustrate the importance of understanding conductor sizing and ampacity, consider the following example. Suppose a commercial building requires a 600 amp service. According to the National Electrical Code, the minimum conductor size for a single copper conductor per phase would be 900 kc mil, assuming a typical insulation type and installation condition. However, if the design calls for parallel conductors, the engineer must ensure that the combined ampacity of the parallel conductors equals or exceeds 600 amps. For instance, 3 parallel 3/0 copper conductors per phase might seem like a viable option. However, as discussed earlier, the ampacity of a single 3/0 copper conductor is typically less than 200 amps. Therefore, 3 parallel 3/0 copper conductors would only provide a combined ampacity of around 600 amps, which is barely sufficient and might not meet the requirements of the local authority having jurisdiction, which may have stricter interpretations of the National Electrical Code or additional requirement. A more appropriate solution might be to use 2 parallel 500 kc mil copper conductors per phase. Each 500 kc mil conductor typically has an ampacity of around 380 amps, resulting in a combined ampacity of 760 amps, which provides a comfortable margin above the required 600 amps and meets most National Electrical Code and local code requirements. In addition to ampacity, other factors must be considered when selecting conductors for parallel installations. These factors include voltage drop, impedance, and fault current carrying capacity. Voltage drop refers to the reduction in voltage along the length of the conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code provides guidelines for calculating voltage drop and recommends that it should not exceed 3% for branch circuits and 5% for feeders. When using parallel conductors, the voltage drop is reduced because the current is divided among the conductors, effectively reducing the resistance of the circuit. Impedance is the total opposition to current flow in an alternating current circuit. It includes resistance, inductive reactance, and capacitive reactance. High impedance can limit the amount of current that can flow in a circuit, which can affect the performance of equipment. The National Electrical Code requires that the impedance of parallel conductors be balanced to ensure that the current is evenly distributed among them. Fault current carrying capacity refers to the ability of a conductor to withstand the high currents that flow during a short circuit or ground fault. The National Electrical Code requires that conductors have sufficient fault current carrying capacity to protect equipment and prevent fires. When using parallel conductors, the fault current is divided among the conductors, reducing the stress on each individual conductor. However, it is important to ensure that the combined fault current carrying capacity of the parallel conductors is sufficient to handle the maximum available fault current. Another important consideration when working with parallel conductors is the proper termination and splicing techniques. The National Electrical Code requires that all conductors be properly terminated and spliced to ensure a reliable and safe connection. When using parallel conductors, it is crucial to ensure that all connections are made properly and that the conductors are evenly distributed among the terminals or spliced connectors. Improper connections can lead to overheating, arcing, and even fire. To summarize the key points regarding parallel conductors and the National Electrical Code requirements, firstly, the National Electrical Code mandates that the ampacity of conductors must be sufficient to carry the intended load. Secondly, when using parallel conductors, the combined ampacity of the parallel conductors must equal or exceed the required ampacity of the service. Thirdly, the circular mill area of the parallel conductors must be equivalent to or greater than that of a single conductor that could handle the load. Fourthly, other factors to consider include voltage drop, impedance, and fault current carrying capacity. Fifthly, proper termination and splicing techniques are essential for ensuring a reliable and safe connection. Sixthly, always consult the National Electrical Code tables and local authorities to ensure compliance with all applicable regulations. Seventh, neglecting to adhere to the National Electrical Code requirements can have serious consequences, including electrical hazards, equipment damage, and potential liability. Therefore, it is crucial to understand the National Electrical Code's provisions and to follow them meticulously. The information presented here is intended for educational purposes only and should not be considered a substitute for professional advice. Electrical work should always be performed by qualified and licensed electricians who are familiar with the National Electrical Code and local regulations. The improper electrical installations can be dangerous and can lead to serious injury or death. The National Electrical Code is a comprehensive document that covers a wide range of electrical topics. It is updated every 3 years to reflect the latest advancements in technology and safety practices. It is essential for all electrical professionals to stay up to date with the latest edition of the National Electrical Code and to understand its provisions thoroughly. In addition to the National Electrical Code, many other standards and regulations govern electrical installations. These standards and regulations may be issued by organizations such as the Institute of Electrical and Electronics Engineers, the National Fire Protection Association, and the Occupational Safety and Health Administration. It is important to be familiar with all applicable standards and regulations to ensure that electrical installations are performed safely and in compliance with all applicable requirements. In conclusion, understanding the National Electrical Code requirements for parallel conductors is crucial for ensuring the safe and reliable operation of electrical systems. Proper conductor sizing, termination, and splicing techniques are essential for preventing electrical hazards and equipment damage. Always consult the National Electrical Code tables and local authorities to ensure compliance with all applicable regulations. The topic of conductor ampacity and the National Electrical Code often leads to questions about dating factors. Dating factors are adjustments to the allowable ampacity of a conductor to account for factors such as ambient temperature, the number of conductors in a raceway, and the presence of other heat-generating equipment. The National Electrical Code provides tables and guidelines for applying dating factors to ensure that conductors do not overheat and that their insulation does not degrade. For example, if conductors are installed in an area with a high ambient temperature, their ampacity must be derated to account for the increased heat. Similarly, if multiple conductors are installed in the same raceway, their ampacity must be derated to account for the increased heat generated by the conductors. The derating factors are based on the conductor's insulation type and the specific conditions of the installation. It is important to apply the correct derating factors to ensure that conductors are not overloaded and that they can safely carry the intended load. Another important consideration when selecting conductors is the type of insulation. The National Electrical Code recognizes several different types of insulation, each with its own temperature rating and other characteristics. The insulation type must be appropriate for the environment in which the conductor will be installed. For example, some insulation types are resistant to moisture, oil, and chemicals, while others are not. The National Electrical Code provides tables that specify the allowable insulation types for different applications. It is important to select the correct insulation type to ensure that the conductor will perform reliably and safely over its intended lifespan. The National Electrical Code also addresses the issue of conductor identification. Conductors must be properly identified to ensure that they are connected to the correct terminals and that they are not accidentally mixed up with other conductors. The National Electrical Code requires that all conductors be color-coded or marked with a tag or label to indicate their function. For example, grounded conductors must be identified with a white or gray color, while ungrounded conductors must be identified with a different color. Equipment grounding conductors must be identified with a green color or a green color with one or more yellow stripes. Proper conductor identification is essential for preventing electrical hazards and ensuring that electrical systems are installed and maintained correctly. The National Electrical Code is a complex and comprehensive document that covers a wide range of electrical topics. It is essential for all electrical professionals to have a thorough understanding of the National Electrical Code and to stay up to date with the latest edition. The National Electrical Code is not a static document, and it is constantly evolving to reflect the latest advancements in technology and safety practices. By staying informed and following the National Electrical Code requirements, electrical professionals can ensure that electrical installations are performed safely and in compliance with all applicable regulations.